morning or good afternoon. We're gonna rock on to Electric Avenue. All right, that's enough of that. So a little review from last week here. We have a simple circuit. We've got the voltage from the battery. We've got something in the circuit, a light bulb, which we're going to say it has a certain amount of resistance to the flow. And we're measuring the current here. And this battery has a voltage of 10 volts, and the current is 1 amp. And if we click on the bulb, it's got 10 ohms. So we've got some relationships going on here that we're going to look at today. Most of the answers you put on the labs last week were spot on, so awesome. So let's keep moving through this. Voltage is the energy in the battery, or the energy in any power supply. It also comes out of our wall outlets. And the more voltage, the greater the ability for it to push charges through the circuit. So if I change the voltage again, it's going faster and faster and faster. And if we go whipping up here, that's going really fast. And so the current's going faster as well. Let's take a look at some common batteries we have around our house. We've got these AA batteries are about 1.5 volts. Same thing with these D cells, but they're going to last longer. The iPhone battery is about 4.7 volts, last a long time too, and they're rechargeable, unlike a lot of these cells here. So these guys are not rechargeable, and this is rechargeable. It has to do with the chemistry involved in the battery, the chemical reaction that's freeing up electrons, and also the way that the battery is built. And the car battery is 12 volts, but has a lot of power. So even though these volts are 12, and it's 3 times the volts or 2.5 times the volts in your iPhone battery, it has a lot more chemical cells inside it, so it can actually generate a lot more current quickly, and eventually we're going to learn a lot more power very quickly than your iPhone battery. So don't try to start your car with 2.5 or 3 iPhones. It's really not going to work. The light bulb has something called resistance in it, and sometimes we look at these goofy little things that we see in electrical circuits, and those are resistors. They kind of control how much current goes through the circuit. If the resistance is really high, so if we make it an infinite resistance, then there is no current. So this gap could be considered a very, 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 very high resistance, where there's no current. And as we can see here, if I increase the resistance, right, you see the brightness going down and the current going down. And if I make the resistance go all the way down to 0, well, I get a fire, right? So we're going to look later on next week at why electrical fires happen and how we regulate those. But I want to give this week a relationship between current and voltage and how we hook things up to circuits in a different manner. One concept we can think about is electrons are lazy. They want to flow through the path of least resistance. They're not really lazy, but they're just, they're going to try to take the easiest path. And when there's multiple paths in a circuit that we're going to look at, sometimes they'll take the easy one, but if that's filled up, they might take the harder one. So we're going to see, hopefully with this simulation, how that can work. So just a little bit of notes for you to scratch down on a piece of paper. There is a little bit of math in this unit, and it's just one formula. It's called Ohm's law. Ohm was a German dude who figured this out, and it describes the relationship between the current, the voltage, and the resistance. And we're already looking at this, that if I increase the voltage in this circuit, then the current goes up. So that's a direct proportion, right? So increase the voltage, increase the current. And conversely, increase the resistance, decrease the current. So those are the concepts. And if we're interested in the math, there's a very straightforward formula. It's the voltage here equals the current times the resistance. It's also written sometimes current equals voltage over resistance. V equals IR. And we call that Ohm's law. And it is not what my wife does in the yoga studio. That is also an ohm. But it's a different kind of ohm. And so that's some math we're going to do. And the math is pretty straightforward. Here's a problem. Here are the units, volts, amps, and ohms. If a light bulb has a resistance of 5 ohms, so let's see this here. If the light bulb has a resistance of 5, so if we put that down here to 5, and basically, you know, the light bulb has a little wire in it, and sometimes they burn out. And if you put too much voltage across the light bulb, it will burn out. And so they're usually rated by how much current I can put into that. So if the maximum current is 10 amps, how much voltage can be applied before the bulb's filament breaks? Well, this thing is kind of cool. If I kind of keep raising the voltage until the current gets to 10, boom, 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 10. So 50 volts. So I've got 5 ohms, and 50 volts will give me a current of 10. Um, so if I look at the math here, V equals IR, that's from the previous slide. I can take my 10 amps, my 5 ohms, and I get 50 volts, and it's kind of working out here. And most of the problems we'll do will have nice round numbers like this. Big important facts that if I were to increase this resistance, I would need more voltage to get that same current. And we're going to look at just some conceptual relationships between these things. So I've changed my circuit a little bit. I've put a switch in here from the left, and if I close that switch, I get the current to flow, just like our light switch on our wall. And I've got 50 volts, and I've got my 5 ohms, so I have 10 amps, and that was a previous math problem. So question for you, if I open the switch, and let's say I want to put another bulb in this circuit like this. And so now I built what's called a series circuit. And if I close the switch, what's going to happen to the current? And that's a good question for us to ask. So all the electrons have to go through both of these guys here. So assuming these bulbs are the same resistance, let's move this guy up to 10, right? I don't want to, oh, no, 5, they were at 5. That's right. So if I break this guy down to 5, assuming they're the same, what's going to happen to the current from the previous path, which was 10 amps. So I'll let you think about that for a second. All right, let's close the switch. Oh, now we're at 10 amps. So the current slowed down. And this is called a series circuit. We call it a series because things are in a path like this. And there are other ways that we can figure this out. But let's figure out the math on this just briefly. If this battery here is 50 volts and I've got 5 amps, I should be able to figure out this 5 and this 5 is 10. So all these electrons have to go through these 10 ohms. So we can look at the math with this as well. And we're going to be doing that in your lab shortly. I wanted to introduce this to you. So this 50 volts equals 5 now times 5 and 5 is 10. So the total resistance over here, let me see if this will work. The total resistance over here is 10 because 5 plus 5 is 10. And so I still have V equals IR. This is a little bit messy, but this 50 here equals 5 times 10. So the total resistance of this circuit is 10 because these electrons both have to go through this 5, and that 5 would be 10. It would be the same if this was 6 and 4 or 3 and 7. The current would be the same. What happens if you unscrew one bulb? Does the current still flow? It's a question you're going to have to ask in the lab. Let you figure that out. Instead of hooking things up in series where it's all in one row, we can hook things up in what's called parallel. And I've got the simulation here on the left. And I've got it disconnected here. But if I connect this guy, I should be able to see that the electricity has this path, so this circuit to go around, and it also has this circuit to go around. So in a parallel circuit, we have multiple paths to travel. Let's see what happens here. Oh, that's awesome. So both bulbs are glowing. I reduced the light bulb here is at 10 volts. I mean, the battery's at 10 volts. and each bulb is at, let me see what the resistance of each bulb is. That's 5 and that's 5. So this is kind of interesting. So the way the energy goes in these circuits, these electrons that are coming up this path are bringing all of that 10 volts. So some of the electrons you can see at this junction here, some of them, let's see if we can zoom into this here. I don't know if we can. No, we can't. Some of the electrons are going in this path, and some of the electrons are going in this path. It's kind of like if you're going to a movie theater and there's a lot of ticket takers or a lot of doors. You know, some people might go through one door, some people might go through the other door, but in both cases, you've got to pay the same amount of money. So these people or these electrons that are bringing their 10 volts, they're giving all their 10 volts to this bulb, or they're giving all their 10 volts to that bulb. So if I were to take a voltmeter, which is kind of fun to do, and I put it here and here, and this is what we're going to do in the lab, I can see that this, let me move this a little bit, this light bulb is getting 10 volts. And if I put this guy over here, I can see that this light bulb's getting 10 volts. So 10 volts to this bulb, 10 volts to that bulb, 10 volts coming out of the battery. Let's see what this current is for this bulb. This current is 2, which makes sense. It's 10 divided by 5. And this current is 2. So this current is 2 amps. This current is 2 amps. The battery has to be providing 4 amps because 2 are going up this path and 2 are going that path. So we call this conservation of charge or conservation of current. 4, 4, 4, 4, 2, and 2. When they come back together, 4, 4, 4, 4. So all the 2 here is going into this battery and 2 is coming out. Now these electrons down here have the 10 volts and these ones don't have any anymore. They gave it all to the bulb. So 2 amps, and then 4 because we're going over here. So let's change this bulb now to, let's say, a lower resistance, right? Let's go down to 1 ohm, right? See what's happening here. So this bulb still getting 2 amps, right? It's still, its resistance is defining how much current it gets. So he's getting 2. This one you can see, right? 10 amps, right? Because this bulb, I broke its resistance down to 1 ohm, so less resistance. So we're going to get a lot more current. So this is 10 amps to this bulb. We've got 2 amps to that bulb. The total better be 10 and 2 is 12 if my math works. Yep, 12 is here, 12 is there. Both bulbs are still getting 10 volts, right? The electrons don't have any more than 10 volts because this battery is only giving us 10 volts. Question happens. What happens if I unscrew a bulb, right? And you could probably figure that out in the lab. So we're going to spend some time in this lab building circuits like this and doing some math and asking some questions. I hope it somewhat enjoyable. And after this, we're going to move into kind of how our homes are wired and how electricity is delivered to us in our daily lives. And there will be a little math involved, but that's okay. It's just V equals IR, and we'll figure that out. Keep smiling out there, Lime Old Lime High School.